Hello, my name is Emma Alexander, and today I'm going to share some joint work conducted at UC Berkeley, University of Toronto, and University of Tübingen on self-motion cues in the natural habitat of zebrafish, which support a lower visual field bias. Larval zebrafish exist in a very complicated environment that is full of forces beyond their control, and one of their most basic behaviors is self-stabilization. This behavior is visually driven, so if you put the larval fish up against a striped pattern that moves, it will swim along with the stripes. This is called the optomotor response, and it is a well-documented phenomenon. But in the natural environment, things are more complicated. Motion cues will be uneven across the visual field due to texture availability, scene depth, and environmental motion, like swaying vegetation, suspended particles, light patterns refracted by the moving surface of the water, and other animals' locomotion. So visual self-stabilization in the natural world is a complicated task. One clue about how they're solving these problems is a lower field bias, discovered last year by experimenters who placed larval zebrafish into a cylindrical arena that could display moving stripes on its walls. This stimulus convinces the fish that they are falling behind and need to swim to keep up. When these stripes were shown in either the upper or lower visual field, the lower field evoked a much stronger behavioral response. Specifically, shown in yellow, the lower visual field evoked a mean optomotor response of about 10 tail beats per second, attempting to keep up with the stripes, whereas in blue, the upper visual field stimulus generated a much weaker response. We hypothesize that this lower field bias reflects an adaptation for effective self-motion estimation from the visual cues that are available in the natural habitat of zebrafish. So let's start out with the basic theoretical question of where a fish should look to determine how it moves. There are a lot of ways to address this, but we'll start out with an illustrative example. We can model the self-motion estimation task by performing a linear regression on flow samples that are modeled from local regions across the visual field. So these are just your standard optical flow patches for different locations and velocities. Now, because forward motion is a particularly important behavior, the metric that we'll use to address the quality of our motion estimation will be the root mean squared error on forward speed estimation from this local flow patch regression model. So if we just put this simulated fish in the middle of a sphere with high quality texture everywhere, this method will find that if we move our sample patch across all azimuths and elevations, we will find our most reliable information at the focus of expansion at the nose of the fish and the focus of contraction at the tail. This pattern is a very solid signature for forward motion, and our model picks up on that. However, this is only true in a really nice, clean simulation of these flow fields. So that was for a high SNR sample. But if we have noisy data, the small magnitude of signal at those foci makes them more vulnerable. And so in a low SNR environment, we actually see that we should exactly avoid the focus of expansion and contraction. And that's only in a sphere with texture everywhere. If we consider an environment that is more like a textured floor, we now find that above the horizon there is no useful texture information, which again changes where we should look. Even the behavior of the fish can affect where we should look. So let's see what happens when our fish is swimming in a straight line, so pure forward translation, but it's being swept sideways by a current. In this 2D motion case, we can see that anywhere outside of certain regions on the equator will give decent motion estimations. However, if the fish combines rotation with translation, as many swimming animals do, we will now see that there are large patches of possible confusion between rotation and translation on the sides of the animal. So when we ask where to look to judge forward motion, we find that we can get just about any answer. Depending on the circumstance, we should look at the foci, or anywhere but the foci, or maybe the upper or lower field is fine, or maybe we should only look at the lower field. And which of these answers applies is going to depend on a lot of variables, from the noise, which is in turn determined by factors like lack of texture contrast, misleading motion samples due to violations of the brightness constancy assumption, and even receptive field size and structure. Additionally, scene geometry and even swimming behavior will play a role. So ultimately, there's no single answer to the question of where to look to judge self-motion. It's inherently data-driven, which means we need to look at some data. So the team went out with a high frame rate, 360-degree waterproof video camera, put that on the arm of a custom robot that can do controlled translation and rotation trajectories, and brought that setup to 8 natural habitats in the native environment of the zebrafish. So here's an example clip from the dataset, just to get you oriented. Within the plastic dive case, you can see there's vegetation, there is sunlight saturating the upper visual field and dappling the lower field. You can see a bit of the texture of the water surface and the scene above it. This illumination environment violates the common assumptions of brightness constancy, as does the reduction in contrast and colorfulness that occurs as objects become more distant. This happens because light is absorbed and scattered more underwater than it is in air. Additionally, there are some systematic differences in scene content and location for underwater scenes that we can explore by calibrating the camera and reprojecting these images onto rectified coordinates. So if we take a sample frame, parameterized by even steps in azimuth and elevation, we can begin to explore these spatial variations in signal and noise in the typical aquatic environment. So you can see that the upper visual field is largely cut off by the dive case, and it's also pretty saturated by strong sunlight in our dataset. So we'll be considering elevations only up to the waterline. That's fixed at about plus 40 degrees by refraction through the water surface in a phenomenon known as Snell's window. And between the waterline and the equator or midline, you can see that some of this image content is reflected. So we actually end up with more texture in the upper visual field than we might in a terrestrial environment with the same vegetation. This is good news for self-motion estimation because it leads to a denser availability of flow samples. And then in the lower field, you see we have a lot of really good texture from the floor, but we also have these sunlight patterns called caustics, and they create false motion signals as they move across the scene. So at different elevations in the aquatic environment, we have unique systematic advantages and challenges in the visual cues available. And the first way that we're going to quantify this is to consider where the texture information is located across these scenes. So we consider 400 frames at each of the sites at 12 elevations, from minus 70 to plus 40 degrees. So here's what the gradient magnitudes from this frame look like. And combining over all of the sites in our dataset, we'll look at the median gradient magnitude across these elevations. And we find that in general, there is more texture information in the lower visual field. While there is high variance both within and between sites, this is our first confirmation that the natural environment supports the lower field bias in the zebrafish's behavior. You can see, though, that there's a major exception to this trend at plus 40 degrees, where the dark to bright transition at the waterline generates a really large image gradient. This is a very strong and consistent scene feature that is governed by the refractive surface of the water rather than the motion of the camera. And so it provides a high contrast edge that is nonetheless uninformative for the self-stabilization task. This emphasizes that while texture content is a mainstay of natural scene statistics, it isn't ultimately what we care about for this behavior. What we care about is where the motion information is available and reliable. So we take 3 velocities, again over 400 frames at 6 elevations, now from minus 60 to plus 40 degrees. We have a left camera and a right camera, and I'm going to show you some flow field examples here, with a color map where the hue indicates the direction of motion and the saturation indicates the speed. So here's an example frame for the fish moving forward. In the right camera, things move to the right, shown in cyan, except in white patches where flow information is not available, or in other colors where environmental motion is giving a misleading signal. And on the left, things move to the left in red. In this clockwise rotation sample, everything appears to move to the left in both cameras. Again, except where motion cues are absent or false. And when the cameras move to the left, we have a focus of expansion in the left camera, with green upward motion above the equator and purple downward motion below it, along with the corresponding focus of contraction on the right. So we take these binocular pairs, and again, just like before, train a linear regression model to determine self-motion. And now our figure of merit will be the RMS error on all 3 dimensions of the velocities in question, now for 50 trial splits over the 400 frames from each site. And we'll plot that RMS error across the sampled velocity, and we'll see that sure enough, the lower visual field provides much lower error estimates compared to the upper visual field. This looks like a pretty good explanation for the behavior that we saw at the beginning. One last thing we want to check is that those matched elevation binocular pairs are only a small subset of the possible flow patch pairs. Perhaps there is an advantage to looking down in one eye and at the equator in the other. But when we consider these mixed patch pairs at one of our sites, we find that looking down in both eyes is advantageous. So to summarize, what we found is that the behavioral bias toward the lower visual field is not an inherent consequence of the problem of estimating self-motion, but is instead dependent on and supported by the natural scene statistics of the native environment of these animals. Thank you for listening, and thanks to my collaborators for their work on this project.